The next speaker is Otto van Koert from Hokkaido. And he will talk about linearized contact homology of connected sums.
Thank you for the invitation, and thank you for inviting me to such a nice place. Okay, so I will be talking about linearized contact homology of connected sums, and I will use contact homology. I will use a little bit more structure of contact homology. So I will start by giving a second introduction to contact homology, if you want. Okay, so let M psi, which is the kernel of a one-form alpha, be a contact manifold. So this is a coorientable contact manifold. And as we have seen already many times today, that means that alpha wedge d alpha to the end, okay, this is 2n plus 1, is non-vanishing. And if you have that, then define the rape field of alpha by the following two equations. So this was already Miguel's lecture. Okay, and so what we're going to do is we're going to define this invariant of contact manifolds, and it's a kind of it's a kind of Floer-like invariant, and the ingredients are the following. Okay, so we first define an action functional, and so for each smooth loop in M, we assign the following number. We just integrate the contact form alpha over this loop. And the claim is that the critical points of A are periodic rape orbits. And okay, so what's the idea of contact homology? So roughly speaking, the idea is that it's the action functional. It's the Morse homology of this action functional. So the idea is cylindrical contact homology. So contact homology comes in many versions, and I will discuss those. Cylindrical contact homology is, well, the Morse homology, if you want, just as in Alex's talk. Morse homology of A. Well, I have a different A than Alex's A, but okay. Okay, so what shall I do next? Okay, so if we want to do Morse homology, what we need to do, we need to look at the flow equation, and for that, let me first choose some auxiliary data. So choose a compatible complex structure J for the symplectic bundle psi d alpha. So J squared is -1, and this should be a metric. And then, of course, we get a metric. We get a metric G, a metric on M, G, which is alpha tensor alpha plus d alpha, and then d alpha with J inserted into the second slot. And that's a metric on M. And then you get an L2 metric, associated L2 metric on the loop space. And now the idea is that you just write down the flow equations with respect to this metric. If you do that, you get a PDE for a cylinder connecting, critical points, so connecting two rape orbits. But if you do that, it becomes rather nasty, and so instead you, so the flow equation is not so nice PDE. And what you do instead is you extend the flow equation to a PD not on M, but rather on R times M. And you do this by first extending the complex structure, the complex structure to an almost complex structure on R times N. So note that this is a symplectic manifold with a symplectic form d e to the t alpha. And how we do this? Well, we just require that j times d dt, so this is the coordinate on the r direction. This should be the rape field. And of course, if it's a complex structure, then this determines j completely. So by abuse of notation, I will keep writing j, although from now on I will mean the j on r times m. Now, so this flow equation, so this extended flow equation will look as follows. So what do we have? So we have it's a map, so it's a cylinder into r times m, and it satisfies the following equation. So if I use coordinates rho and psi here, then it should satisfy the following equation. And of course, since it's a kind of flow equation for Morse homology, we have the following asymptotic convergence conditions. Where gamma plus minus are closed, are periodic rape orbits. So I should say that the parameterization is not the usual parameterization. I parameterize them by action such that this holds. Okay, so the picture that you have is, of course, that I have, so this is m, this is the r direction, is that I'm now looking at, holomorphic curves going from one rape orbit to another rape orbit. And it's useful to at this point, so if you do Morse homology, you will stick to these kind of, to this flow equation, but it's useful to already, at this point, discuss another kind of flow equation. So, other flow equation. So, more general flow equation. And which is the following. So we let sigma be a punctured sphere, and we take a point P out and a number of points Q1 up to QK. And so later on the roles will be a bit different between P and Q. And so the flow equation will be then as follows. So U tilde is a map from sigma to r times m, and I require the following. It should still be a holomorphic curve, so it should satisfy this equation. Okay, so it is a complex structure J, say. Complex structure, small j. And well, we require similar convergence as before. And by that I mean that if we go to P, you can kind of choose cylindrical coordinates such that this thing holds. And if you go to Q, you have similar coordinates. So near P, a convergence to to some periodic orbit at plus infinity, and near the Q's convergence to periodic orbits at minus infinity. So, well, if I draw the picture, well, they still include cylinders, but there could be like a pair of pans, or actually anything can happen. Also, planes, I should add that I also consider planes. And okay, so what we're going to do now is we collect solutions to this, well, kind of flow equation, to this flow equation star in a moduli space. So we collect the solutions to star in a moduli space. And so we put m gamma plus, gamma 1 minus, up to gamma q minus, gamma k minus. These are the solutions to this flow equation star up to parameterization. And so, okay, so this problem is a Fredholm problem, and so you can, or you can compute the index, and if the situation is nice, then actually this is a smooth manifold with dimension equal to the Fredholm index. So I say the virtual dimension, and whether it coincides with the real dimension or whether this is a manifold is a different question. But the virtual dimension is defined as follows. This is given by well, the difference of the reduced Conditzer indices. So, well, Miguel already talked about this, and he didn't define it, and I won't define it either. So, no, sorry. So, but yeah, as you already saw, it is a kind of winding number. That's maybe a good way to think of it. Okay, so, well, if J is regular, nice if you want, then these moduli spaces are smooth manifolds of dimension equal to the virtual dimension. So whether it's another question whether these regular J's exist, but okay, I'll keep it at this. Now, so if we just pretend that this works, then of course we are in good shape to define kind of a Morse homology for the action functional, because we can just copy the dimension formula does actually quite exactly what we expected it to do. So if we define a chain complex for the context manifold M as this is a, we'll say, graded Z2 vector space generated by well, by the critical points of this action functional, so by periodic orbits, then the differential for cylindrical contact homology is defined as follows, is given by. So, okay, I just want to write down the formula once. It's kind of well-known formula in a sense. So we count over all rape orbits that have index 1 less, and then we count the number of elements in the moduli space gamma A, gamma B, and now notice that I extended. Is it still there? Yes, I extended this. But if I do it this way, it's actually the J is actually translation invariant. So if I have a solution, and then I get if I have one solution, then I get a new solution by simply adding a constant C to the A coordinate there. So the zero-dimensional moduli space is actually the one-dimensional moduli space, and so I need to mod out by this R action. That's what I will do. And here this counting, yeah, so this is kind of tricky, because in general you shouldn't use the two coefficients, and then this counting operator is kind of more complicated. It doesn't, so there's a sign involved, and there are some numerical constants, but let's forget about this for now. Okay, and as mentioned, this is D. And And as mentioned already before, it's a kind of, it's a theorem of Eliasberg, or given to Hohenhofer if you want. So that d square is 0, and if the chain complex vanishes in degree -1, 0, and 1, then d square is 0, and the cylindrical contact homology, defined as the homology of the chain complex D, so maybe I should call this D cylindrical, defines an invariant of M psi. So let me give you some rough ideas on the proof. So as usual, you try to identify d squared with the number of boundary points of one-dimensional moduli spaces. The idea is d squared counts the number of boundary points of one-dimensional moduli spaces. And here, of course, so at this point I should say that I assume that I have kind of a regular J, so that this virtual dimension makes sense. The virtual dimension is the real dimension. And well, later on I make some remarks on to what extent this is true and what you can do about this. Okay, so if you have this, this is what we want to show, but there's a kind of obstruction, and that's the following. So in Morse homology, of course, if you take a sequence of trajectories, of gradient flow trajectories, in the limit it will consist of pieces of gradient flow trajectories. But here that doesn't need to be true. So sequence of cylinders might degenerate in other ways. And so the basic example is that, well, maybe a cylinder looks like this, and if I go further in the family, then maybe it breaks not as a cylinder, but rather as a pair of pans capped off by a plane, and then another cylinder. So this could also happen. And if this happens, this would be it would lie in the boundary of the moduli space, but this is certainly not counted by d squared. On the other hand, if I know the following: if this is a one-dimensional family, then I know the index should be 2. Well, since I assume this here, and well, since this index is additive, I need to spread them here. And if I assume that J is regular, the index must be non-negative to ensure that there is actually a holomorphic curve. So this would be a possible division, and you can look at other divisions, but then you see quickly that other options do not appear, because actually if I put here, for instance, a 0 and here a 2, then certainly this could exist. This can also exist because there are always vertical cylinders in a symplectization, but this one shouldn't exist. Okay, well, this would certainly be fine, but if I have an index 1 family of planes, then there is a rape orbit of index of degree 1. But I excluded such a thing. So C1 is 0 implies d squared is 0. And similarly, so this is the argument for d squared is 0. So why do you need the other conditions? Well, you need also to show invariance. You need to show that you have a kind of chain map property. If you have two different forms representing the certain contact manifold, then I can connect them by a symplectic cobordism, and you want them to construct a chain map from one complex to the other. We do it basically in the same way by defining it by such a formula. So you want to show that it's a chain map, and then you run into the same problem, and you can solve it by requiring this one. And then there's a homotopy arguments. If you're familiar with this story, then I guess this is a kind of sketch on how this should work. No. Okay, so now you're stuck with this rather strange condition that there shouldn't be any orbits of this degree, and there's kind of solution to that. So, and this is contact homology algebra. And so what's that? So the idea is here that that this problem appeared since we were looking just at cylinders and we don't count pair of pans. So, but if we instead count kind of tree-like curves, well, if you take a sequence of trees, it will always break as a tree. So then you count them anyway. So that's the idea here. So we define A star to be the graded algebra generated by closed grape orbits. So I write it grid A. And then, so elements are of the form, elements are linear combinations of products of grape orbits. Okay, so we define then the differential as follows. We define it on generators, and then we extend linearly and by Leibniz rule to describe what it does on products. And it works as follows. We count all kinds of tuples such that, the dimension of the moduli space mod the R action is 0. So then we have gamma A. No, it doesn't fit. Okay. Okay, I'm just a little bit too lazy to write down the exact condition for the indices. It's over there. You just use the dimension formula. So the sum of the degrees of the gamma b's should be one less than the degree of gamma A. Okay. So this is how you do it on generators, and then you extend linearly and by Leibniz rule. So then, this again a theorem, also Eliasberg, Giventhal, and Hofer, and that d squared is 0, and the contact homology, defined as the homology of this chain complex, is an invariant of m psi. Now, okay, so now we don't have a problem that this isn't defined in certain degrees, or only if we meet some conditions on the degree. But we are actually stuck with another problem that this is much harder to compute. Because we count now everything, or almost, we count all trees, and then there's much more to compute. So the idea for this is now to kind of linearize this theory, and that's linearized contact homology. And I've explained the ingredients for for the title of my talk. So linearized contact homology. So the idea is that if we write D as follows, so we write D as d0 plus d1 plus d2, where the subscript indicates the number of negative punctures. So this counts planes, this would count cylinders, this would count pair of pens, and so on. Now, if we write d squared is 0, in these components, and what we get is the following. We get d squared, d0 squared is 0. We get d0 composed d1 plus d1 composed d0 is 0. And we get d0 composed d2 plus d1 squared plus d2 d0 is 0. Now, observe the following, that, okay, d0 squared is 0, but if we instead have that d0 itself is 0, so there are no planes to count, then this equation drops out, this one drops out, and this one reduces to d1 squared is 0, meaning that d1 is a differential. Of course, I'm not saying anything surprising because, well, this excludes kind of planes of that could be counted by the differential. But now the idea is the following, that the idea now is to find a coordinate transformation such that the transformed differential satisfies, we'll say, well, d tilde 0 is 0. And for that, we have the following notion. So, definition, a homomorphism epsilon from the algebra, so from the chain on chain level to the base ring, so here we have Z2, but in general just the base ring, is called an augmentation if it commutes with the differential, so if it's a chain map if you want. Now, let me first argue that, that augmentations exist. Sometimes. So proposition, if M alpha is strongly symplectically fillable by, say, W omega, then we can define an augmentation as follows. We just define it as, okay, we send every Rape orbit to the number of rigid planes, so zero-dimensional families bounding gamma A. And so this is then is an augmentation. Okay. Now, so well, there are many contact manifolds that have this property. So let's assume now that we have an augmentation, and then what you can do is the following: given an augmentation, we define an algebra automorphism phi of epsilon as follows. On generators, we just put it equal to, well, phi epsilon of A is A plus epsilon of A. So in many cases, if this is a generator and not in degree 0, it will just be 0. And I should maybe it should be equal to A if A is, well, it's in the base ring. Okay, so I will write Z2, so now it's a bit silly maybe if I write it like this. But in general, you write this, replace Z2 by base ring, and then it's a more sensible statement. Okay, so now with this algebra automorphism, and now define the transform differential. This will be our coordinate transformation, and we define the transform differential as follows. And I claim that epsilon 0 is 0. Actually, if you write down the number of negative punctures of this thing, then you can actually see that in degrees, so the number of if there are no negative punctures, then the contribution is exactly this. And so, since we have chosen augmentation, it vanishes. Okay, and so now we have a definition. Because if we have this, it follows that D1 is already a differential, and therefore we can define the linearized contact homology as follows. Define the linearized contact homology of M alpha with respect to the augmentation epsilon is given by this is just notation. Yeah, so now I cheat a little bit in my notation. So before we had we had defined this algebra, but now actually, since this doesn't increase the number of it keeps the number of terms in a product, and so in particular, if we start with just linear combination of Rape orbits, and we apply this one, we keep a linear combination of Rape orbits. So we don't need to use the algebra here, but rather the module or a vector space generated by periodic Rape orbits. And so I write C instead. Yes. Okay. And okay, so this isn't defined in many more cases than in just and there's not as many obstructions as for cylindrical contact homology. But it is also a disadvantage, another one. So it's maybe it's not always defined as is the algebra, but it's defined in more cases than the cylindrical homology. On the other hand, and this is maybe a warning, it's not an invariant anymore. Linearized contact. So it does depend on the augmentation. No. It's still convenient to work with this because it has it behaves well under certain operations, and the cylindrical contact homology also does, but it's kind of more restricted. The algebra does not behave as well, unfortunately. Okay, so maybe some remarks on the regular J, which because I kind of needed it, I assumed this, and then okay. So remarks. In general, regular J do not exist due to problems of multiply covered curves. So this sounds maybe very strange because, yeah, in Morse homology certainly by a small perturbation you can achieve the more snail condition. And here the analogous statement does not, so if in Fleur homology you would perturb J, and then you get a regular J, and then it works. But here it's not like that. Well, in Fleur homology there are also more complicated situation, of course. And so maybe a good example to think of is if you have a vertical cylinder, which always exists, I can look at branched covers, and if you then look at the dimension formula, well, if the index iterates in certain ways, then in some cases there shouldn't be branched covers, so there shouldn't be curves like this, where this is gamma 1, with multiplicity 2, and here gamma 1, here gamma 1. So if it depends on how the rate, the Conditiner index increases, and there shouldn't be such things, but there are always such things, because I can simply take a branch cover over a vertical cylinder. So this kind of shows that you cannot achieve a regular J transversality by choosing a regular J. Instead, so need a new perturbation scheme. And unfortunately, this new perturbation scheme is still in development. So it's this polyfold theory, for instance, of Hofer, Vysotsky, and Sander. So there are also other approaches, but I don't know so much about them. Oh, I don't know so much about this approach either, actually. Instead, let me just mention one case where you can do a little bit more. So, so definition, a contact manifold M alpha is called index positive if there are constants C1 positive and C2 such that the Conditiner, or the degree rather, I can also say Conditiner index, it doesn't matter actually, is larger than a constant times the action plus this constant C2 for all rape trajectories gamma. And well, it has some nice properties. So index positivity is preserved. Under connected sums, and also other kinds of surgery. And now, yeah, there's another remark. So I don't want to be too precise. So many cases, in many cases of index positive contact manifolds, well, transversality, so making sense of this dimension formula can be achieved. Well, in the sense that well, the cylindrical contact homology is okay. Okay. No questions. Okay. So the index positivity condition will be useful later on as well. So, yes. For everything. Yeah, because so if you I mean, so okay, so the transversality condition, you need a kind of good enough growth for just closed orbits, but to get this, you need it for all trajectories. And yes, for trajectories, and you need additional. You need first that you need a kind of global trivialization of the context structure, so that already excludes many contact manifolds. And then so you always compute with respect to this global trivialization. And okay, and then you could say, well, does it then not depend on the trivialization? Well, it in a sense does for trajectories, but for closed drape orbits it doesn't matter actually. But of course, the conditions to have a global trivialization of the context structure already implies a lot. And actually, I need to really make it work. I need that the manifold is actually simply connected. Otherwise, it doesn't work. But these kind of technical things, I don't know to talk about it today, at least. So how much time do I still have left? 20 minutes. Okay. Okay, so let me now come to linearized contact homology of connected sums. And at this point, I should mention that everything is joint work with Frédéric Bourgeois. So let me first describe how you define connected sums for contact manifolds, because it's necessary for the construction. So let M1, M2 be contact manifolds, and choose for connected sums Darboux balls di in mi. So these Darboux balls will be used to construct the connected sum. And so the first step is to embed these Darboux balls, both of them in R2n. So as kind of contact type hypersurfaces. Okay, so the picture will be as follows. So we have R2n with the symplectic form dx, dy, plus dz, dw. And well, I embed the Darboux ball just as a plane at w is 1. So this is the w coordinates, and here are the x, y, and z coordinates. And here I embed d2 at w is -1. And note that the Liouville vector field say x. So the following Liouville vector fields, this is kind of what you would expect for a sphere, but here's kind of a strange version. Induces the standard contact forms. So this Liouville vector field looks like this. And if you insert it into omega, you get the standard contact form. And actually, with this one, you get the one with the opposite orientation, as you shoot for a connected sum. Induces the standard contact forms. So the next step is, of course, to glue or glue the Darboux balls together. And so what's this? This is, well, I call it a connecting tube, and it's given by the set f is 1, where f is given by the following function: x squared plus y squared plus z squared minus w squared. And so what you really need to do is, of course, to smooth near di. And note that x, the Liouville field x, is still transverse to this tube. So that means that looks like this. So that means that this whole tube, so is then a contact, is a kind of contact manifold. And since far away it induces just a standard form, we can just then define the connected sum of the contact manifolds. Okay, so now some notation. So I will call this always the tube, and there's some important submanifolds of the tube. So W is the set, capital W is the set, small w is 0, so this is the middle of the tube. And S is the set W is 0 and Z is 0, and this is a codimension 2 contact sphere inside the middle. So it's useful to draw the picture, but now rotated by 90 degrees. I'm kind of used to drawing it like this, but it's actually better to draw it like this, because so then here we have this sphere in the middle, which is codimension 1, so that's W, and in the middle of this sphere there's a contact manifold, codimension 2 contact manifold, and this is then this tube. Okay, and now there's the following lemma, because, okay, so what have we done so far? This is just a setup for the connected sum, and now note that actually the symplectization of this of the connected sum of the contact manifold can actually be put inside this model, because instead of putting f is equal to 1, we can put f is equal to the e to the t, and that way we embed the symplectization of this tube inside Cn, and that's very useful. So, okay, let me now come to the following lemma. So, of course, to say something about contact homology of the connected sum, we need to have some kind of control over what holomorphic curves do. So suppose that we knew what they did in M1 and what they did in M2. If we now connect sum them, then maybe they are very strange and go through the tube. But the following lemma says that this is not the case. So let U tilde from some Riemann surface into R times, well, M1 connected sum M2 be a holomorphic curve bounding a collection of Rape orbits capital gamma, then if the linking number of gamma with this codimension 2 sphere is 0, I should maybe use a better notation. So U tilde is A U. So A is the R coordinate and U is the M connected sum M2 coordinate. If that happens, then the image of this holomorphic curve will not intersect capital W. And so the idea is the following. The idea is that the symplectization of the tube, well, and in particular, actually, of W, is filled by almost complex submanifolds. And if actually what happens is, well, bounding S. And what happens if you have a non-empty intersection, then by positivity of intersection you get a positive contribution to the linking number. So positivity of intersection. So holomorphic curves intersect complex submanifolds, almost complex submanifolds of the right codimension in positively. Implies and that's a contradiction. Okay. So that means that holomorphic curves cannot get through unless they have a good reason to get through. Now, let me now describe what we still need to do to say something on the contact homology of connected sums. So now, so the chain. So what's about the chain complex of M1 connected sum M2? So what closed rape orbits do we have in the connected sum? Well, okay, I haven't told you that, but actually this codimension 2 contact sphere contains lots of rape orbits. So I call these rape orbits, so orbits. So this is one type, so they're kind of tube orbits. And those are orbits in S. And you can actually arrange that these orbits have arbitrarily small action by simply squeezing the tube. So now I choose, of course, F is 1, but if I can just take another profile, and by doing that, I can make the action of these tube orbits as small as I want. So small action. So 2, we have, of course, orbits in M2 that were not affected by the connected M1, that were not affected by the connected sum. We have orbits in M2, and we have kind of what I call wandering, or what people call wandering orbits. And so wandering orbits are both in M1 and M2. And so by perturbing kind of the Darboux ball where you glue, you can actually arrange that these orbits have arbitrarily large action. So so you can think of them as large action orbits. Now, so what does this mean? We have this lemma, we have a kind of this description, and we have something on the action. And so I forgot to tell you something. So we use this flow equation. So I told you before about this flow equation. If we really had used the real flow equation, and of course it's clear that it decreases action. But we changed it a little bit. So I should remark at this point we still have a kind of action decreasing property. So so recall holomorphic curves have action decreasing property. So what do I mean by that? Well, the energy of a holomorphic curve, so U is a map from sigma into R times M. The energy of a holomorphic curve is defined as the integral of d alpha over sigma. And well, since we have a since we chose J to be a metric on d alpha, this must be non-negative. On the other hand, if we just evaluate this by Stokes' theorem, then we see that we get the action at the positive end minus the sums of the actions at the negative ends. And so that means that holomorphic curves are action decreasing. And now if you put everything together, we see that we have the following. how much time is still left? Well, okay, then I give you the short version. Okay, the short version is as follows. So what do we have? So these have small action. So I call these tube orbits, and they certainly inject into the chain complex for the linearized contact homology. So let me here at this point make a remark. So I write it down first. So remark. Composing the augmentations with the gluing, with the surgery cobordism gives an augmentation I call this the connected sum augmentation. Okay, so this is a remark that I should have made before, of course. Now if you have that, then actually you can use this surgery cobordism to get the map into, well now I need more space. I erase this. This is just inclusion. So this is the projection by the surgery cobordism. And I claim that this is a short exact sequence by the properties that we, well, by everything that we have done so far. So it's a short exact sequence because, so well, I just write it short, actually I write short exact sequences. It's a short exact sequence because the differential for the connected sum can be reduced as follows to the following form. So, okay. So I told you that these tube orbits have small action, so they cannot go anywhere under the differential. So here are zeros. Then, well, an orbit in M1 could go under the differential to. So here are tube orbits, and this could happen. Well, the lemma told me that holomorphic curves cannot get through if they don't have a linking number, but the tube orbits lie exactly in S, so you cannot define any linking number, and they can actually go there. So this is C1, C2. So then here, well, you should think of it as the differential in M2 and M1 that isn't affected because of the lemma. And here we have no idea what happens. But these have large action, and now if you think of, okay, so the wandering orbits can be ignored for the following reason. So so the argument that I'm working on is kind of a direct limit argument, but I haven't finished that. What if we have index positivity, you can use another argument. Namely, you just perturb such that the orbits have such a large action that the index is large. Large action implies a large degree. So we just, and then we just use invariance of contact homology to get to make sure that they don't matter. Okay, so then we have this short exact sequence, and then of course a short exact sequence gives a long exact sequence in homology. So the sequence is then there is a long exact sequence for connected sums, and it looks as follow. It looks like has the following form. So we have the contact homology of the tube, which is basically the degree shifted version of contact homology of the standard sphere. Then we have the contact homology, the linearized contact homology of the connected sum. and the direct sums of the contact homologies. Okay, we know these maps actually, so I haven't written them down, but this is just the induced inclusion, this is the projection induced by the surgical Bordism, and this is the connecting homomorphism, which you have a rather explicit description of. Okay, thank you for your attention.
Is there any question?
Yeah, so you could apply this to construct many context structures on certain manifolds, maybe S2 times S3 if you want, because what you can do is you can just, well, I mean, you actually don't need the long exact sequence for that, but if you want, you can put it in there, because you just take, well, you take your contact manifold for which basically cylindrical contact homology. So this, I can just, if cylindrical contact homology is, if it has index positivity, then I can really talk about, well, with high enough index, then I can talk about cylindrical contact homologies, and this is a sequence for cylindrical contact homology. And then what I just do is I connect some with an exotic contact sphere, so with an exotic contact structure on a contact sphere, and then you see that you get new generators in a certain degree, and that gives you kind of, that's why you can show that there are different contact structures. But you don't really need this. Maybe it's more interesting to point out that this is a Mayer-Vietoris style sequence, and we expect that this actually works for all kinds of subcritical surgery, and that's maybe a much more interesting point of view. But, okay. Yes? Because actually this one, you don't need this at all, because this one is actually very small, and for some exotic spheres there are so many generators in this degree that this one can never kill them. So that's roughly the idea. So if you don't want to use this long exact sequence, you just say, well, in our connected sum, I know how the chain complex has changed. Okay. And then you just have too many generators that can never be killed by anything else. Okay. Yeah.
More questions?
Wandering orbit.
Yes.
You take a direct limit on degrees or something like that.
And the action. And that's kind of, you
want to say that in each degree eventually everything stabilizes.
Yeah, but okay. So this is, so I have here two arguments. So the second argument is kind of clean and understandable, I think. So what you do is if you just perturb, so you have, if you have one kind of, okay, you have a connected sum, I can now kind of squeeze the tube. If you do that, then these wandering orbits will have larger action. But if I have index positivity, that also means that they have larger index. And then I've just pushed, so suppose that I want to know contact homology in a certain degree window. Then I just squeeze the tube so much that these wandering orbits are outside my degree window. And then I say, well, okay, then I know everything in this window, and then it's okay. Okay, if you don't have index positivity, it's, there's more to be done.
I was wondering whether you can get away with index positivity by just manipulating a little bit the definition, right? Instead of just taking contact homology defined by all orbits,
Yeah.
you just take it as a kind of direct limit.
Yeah.
On the action.
Yes, but okay.
It's still an invariant, and it may not need the index positivity to work for this.
Yeah, so there are several. So a large action orbit could kind of kill if it has low. So let me point out the simplest kind of problem that you have. So suppose that I'm talking about cylindrical contact homology, then and I don't have index positivity. Then actually there could be after connected sum, then there can be orbits with degree -1, 0, and 1, and there could be bounding planes. So they can destroy kind of invariance, and you have no control over them. So, and I mean you can say, well, a direct limit argument, but maybe outside the thing that I'm considering, there might be this thing, and then well, I don't have invariance. So this is kind of the simplest problem. So if I have index positivity, I can sensibly say this is a long exact sequence for cylindrical, And if not, then I have to use the linearized version because I have even no clue. And actually, I think it's, well, okay, maybe I should think about it, but. Yes.
If you have documentation for M1 and M2,
Yes.
would you in general sort of get like algebraic documentation? Probably not.
For connected sum of M1 and M2, or what are you talking about? Yeah. So what you just do is I have a cobord. So the cobord is the surgery cobord is induces a map on chain level from the connected sum to the direct sums of these things. Okay, so I should now talk about the algebra because now I'm talking about the augmentation. And then what you do is simply, okay, this is a chain map. And now if I compose here with the augmentations, if I had an augmentation for M1 and for M2, if I compose with the augmentations, then the whole thing is still a chain map. And that's actually what an augmentation is. It's just a chain map to the base ring. So I still get the chain map to the base ring. Just take the sums of these two things.
More questions? So let's thank Otto again.